So let's get started. On behalf of the Committee of Stochastic Programming, I would like to welcome all of you to our second webinar in our new webinar series, Decision Making in an Uncertain World. I'm Güzin Bayraksan from The Ohio State University. I will be joined by our Twitter account manager, Phoebe Vayanos, but I don't see her now. She will be moderating the questions. Just as a reminder, if you haven't done so yet, you should mute yourself during the talk and save your questions till the end of the talk. And at the end of the talk, we will moderate the questions. You can type them in the chat room, in the chat box, or you can raise your hand in the participant list and we will be moderating the questions. So it is my pleasure to introduce our speaker today, Cynthia Rudin. Cynthia, could you go to the, yep, thank you. She is a professor of computer science, electrical and computer engineering, and statistical science at Duke University. Before Duke, she was at MIT, Columbia, and NYU. And her degrees are from University of Buffalo and Princeton University. She's got many awards over the years. She's a 3-time winner of the Inform's Innovative Applications in Analytics Award. She was named top 40 under 40 by Poets and Quants in 2015. And BusinessInsider.com named her as one of the 12 most impressive professors at MIT. And she served on committees for Inform's, American Statistical Association, DARPA. She's also a fellow of both the American Statistical Association and the Institute of Mathematical Statistics. And we are really very excited and honored to have her give a talk. Just like last time, we're going to start our seminar by asking this very deep question, but we want a short answer. What is your approach to or your view of decision-making under uncertainty? And I will also let her talk about that. And her talk, by the way, is a very important topic: interpretability and explainability in machine learning. So thank you.
Sure. Can you all hear me okay? Can you hear me?
Yeah.
Yes.
Great. Okay. So I guess my view, at least the view that I'm promoting lately, is that we should do decision making in a human aware way where machine learning tools are decision aids to human decision makers rather than having the machine learning tools making the decisions themselves. And there are a lot of really good reasons for that. But in order to do that, you need to have the models be interpretable. So in this talk, I'm going to discuss, I guess, one of the major kind of rifts right now in the machine learning community, which is whether you should design a model that's itself interpretable to a human expert, or whether you should explain a black box. Okay, so I want to start by looking at the world as it is now, where they don't use interpretable machine learning for some really important problems. And what they're using right now are these black box machine learning models. And these are models that are either too complicated for a human to understand, or they're proprietary, which means they're some company's secret sauce. And they hide what the calculation of the model actually is. Okay, and so these are all prediction models. So I want to talk about what happens when you use a black box machine learning model for important problems. Well, one thing that could happen is that you could get several years extra prison time. And this is an example of Glenn Rodriguez, who was sent to prison at a very young age. And he was a model prisoner for like 17 years or something like that. And then he was denied parole. Okay, so why was he denied parole? And the answer was that there was a typographical error in a score sheet that was used as input to a machine learning model called COMPAS that was predicting whether he would commit a crime in the future. And this model had this COMPAS that had 137 factors, and it wasn't easy to spot the error. And the only way he was able to find the problem was because he compared his score sheet afterward to someone else's score sheet, and he noticed the difference. He noticed there was a problem. And so It was too late. He was denied parole. There's nothing he could do about it, and there's a few years extra prison time for someone. Okay, and this, by the way, this particular problem with the typographical errors, we'll talk more about that later because it happens to a lot of people with exactly the same model. Okay, so what else could happen to you as a result of a black box model? Well, if you lived in California during the wildfires of 2018, you might have seen Google's daily air quality index predictions that said it was safe on days when you'd walk outside and there was a layer of ash on your car. So, you know, what went wrong here? Well, it turns out that Google replaced the air quality index from the Environmental Protection Agency. It's a very, interpretable, trustworthy model. They replaced it with this model from this company, Breezometer, which is a proprietary model. And it's not clear what happened, but Breezometer clearly didn't troubleshoot their model carefully enough. And, who knows how many people it affected, right? Who knows how many children went outside to play on those days because their parents looked at looked at Google and said, "Oh, look, it's safe to go outside. You could go outside." And you'd think the layer of ash on the car would have sort of, deterred them, but you really don't know if that really happened. Okay, so another thing that could happen is that you could receive worse health care because of your race. And this article said that a hospital was ranking patients to get additional attention, and the white people got higher rankings even if they were less sick. And it was because the algorithms were using cost information to predict, or they were using cost information to determine who was going to get care. So they would predict what cost you would be. And of course, the black people were receiving lower cost health care, and so this algorithm sort of thought they were less sick and didn't recommend the extra care for them. And of course, I've just given you a few things that have gone wrong with black box models, but there's a tremendous amount more that could go wrong, and there's been a huge amount that probably has gone wrong, and I don't know about it because they, covered it up. But now people are starting to use machine learning for medical decision making and for loan decisions and for self-driving cars and for all matter of things that you really don't want to go wrong. And some people love their black boxes. They argue fiercely that they need them, and so I'm providing kind of the counterpoint to that argument. Okay, so let me give some definitions here. So an interpretable machine learning model, it's a machine learning model, so a predictive model that obeys a domain-specific set of constraints. And I'm going to give you my more technical definition, which is that it's constrained in model form so that it's either useful to someone or obeys some structural knowledge of the domain, such as monotonicity along one of the features, right? Causality constraints, structural or generative constraints, additivity constraints, or physical constraints that come from domain knowledge. And there's a spectrum between these models that are very that can fit on a PowerPoint slide, very interpretable, where all the features, you can see exactly how they're jointly related to each other, to these models that are loosely constrained, where they might just monotonically be forced to decrease along one variable, for instance. So there's a whole spectrum of constraints you might want to include in these models. So I'm going to give an example of how interpretable machine learning really should work. Okay, this is really how it should work and how it does work in this one instance. Okay, so this is a case where we're trying to prevent brain damage in critically ill patients. Okay, so if a patient comes into, this is a hospital, and they have an aneurysm and the aneurysm bursts, they have a hemorrhage in their brain, which is this. This is blood in the patient's brain. And then the patient would go and get surgery and end up in the intensive care unit. Now, these patients who have had traumatic brain injury, they are at high risk for seizures. And brain seizures are awful. They actually cause brain damage. They actually can cause more problems for people than the actual hemorrhage itself. And these are not seizures where people are visibly shaking. This is only in the brain. And in order to even detect these seizures, these patients need to be monitored with EEG, continuous EEG monitors. That's the only way to detect these seizures because you can't see the patient's, what's going on inside the patient's brain. Okay, so the only issue, of course, is that there may not be enough there may not be enough monitors to actually monitor what's going on inside all these patients because there's a limited supply of monitors and they need to be allocated to the people who need them. Um, so you know, there's not enough equipment, there's not enough people to run that equipment, and so you have to allocate it properly. And what ends up happening is people stay on the monitors way too long, and so it prevents the hospital from being able to monitor patients who need it. Okay, so what we did was that we worked with neurologists at Massachusetts General Hospital and the University of Wisconsin, and we developed an interpretable machine learning model called the 2 helps 2B score. And 2 helps 2B is it's a machine learning model, and it's small enough that we can put it on a PowerPoint slide, and it predicts seizure within 6 hours. That's its goal, based on the continuous EEG measurements. Okay, so this is the whole machine learning model. So it's 2 helps 2B because it's 2HELPS and then 2 points for the B. So it's 2 helps 2B. So the doctors can just memorize the model just by knowing its name, because these things are meaningful to doctors. And then once you get the total number of points, it translates into a risk through this table on the bottom here. So if you get 3 points, there's a 50% chance you'll have a seizure within 6 hours. Okay, so let me tell you a little bit more about this model. Um, and so this model is, it actually was not created by doctors. It was created by, you know, most scoring systems like this are created by doctors. This one was not. It was created by data fed into a machine learning algorithm. And it was sort of, you know, over 70 variables fed into this machine learning algorithm that figured out which 6 variables to pick and what the point scores are and how they translate into this risk. It's a machine learning model, even though it looks like a rule of thumb. It's actually a full-blown machine learning model. It's just as accurate as any black box machine learning model you want to use on this data. And it doesn't force you to trust it, right? Doctors can decide themselves whether they want to trust it. And they can also calibrate the score with information not in the database. So if the doctor looks at the patient and says, well, you know, they're getting 1 point for this, 1 point for that, let's give them, you know, an additional 1 point for this other thing that is not in the database that I think is important. The score can be explained to non-physicians so that you can explain to someone's relatives why they're being taken off CEG monitoring, for instance. And so it's serving its full purpose as a machine learning method that's also a decision aid. As I mentioned, there are 6 variables here, but we started out with a database of over 70 variables, so the feature selection was done as part of the algorithm. So now the patient comes in with their burst aneurysm, they have surgery, they are placed on EEG monitoring, the doctor looks at the EEG signal and says, oh, this person has 3 points, 1 for this, 1 for that, 1 for this. So they are placed on continuous EEG monitoring for over 72 hours, at least 72 hours, and they start them on preventative medications. And if their score is very low, they can take the patient off monitoring and give it to someone who needs it. So I'll tell you a little bit about the results so far on 2 helps 2B. So the data set we created was a multi-center cohort, but the doctors tested it, they validated it after the fact on a separate multi-center cohort. And what I'm showing you is predicted versus true. So you want to be kind of along the diagonal there. And the initial data was in blue and the validation data was in green, so you can see that it's nicely right along the diagonal. But also you can see that these values here are sort of staggered equally along this the probability axis, right? There's no bunching of these probabilities, and that was sort of that was done on purpose. That's something that comes out of these machine learning methods, so that you get coverage of the whole spectrum of probabilities. Okay, so far this model has been implemented at 2 hospitals, Wisconsin and MGH, and it has ongoing implementation at several other hospitals, and it's also available online in these, you know, like if you go to medscape.com, it's got millions of scales, and this is, I think, the only one that was actually created by a fully machine learning method, and hospitals use these scores regularly. And so far, the doctors said that in 2018, at these 2 big hospitals, it resulted in a 63% reduction in the duration of EEG monitoring per patient, which allowed them to save some money per patient. But what the real important statistic is that it allowed them to monitor 2.8 times more patients than before. And so this, they say, it has reduced brain damage, serious brain damage, and saved lives. And they gave us a number of estimated savings, but the fact is that this 2.82 is much more important than that number. Okay, so that's how interpretable models are supposed to work, but a lot of people say, okay, but that's so simple, it's got to lose accuracy. So that hasn't really been my experience though, and I'm going to tell you a lot more about why that's, or well, not why that's true, but that it's true. And in particular, I'm going to go back to this example of the 2 helps 2B score, and I want to point out the model that was used to deny the parole of Glenn Rodriguez. It's called COMPAS. COMPAS is run by a company called Northpoint. They charge hundreds of thousands of dollars per jurisdiction, per county, per year to use that software. And I want to talk to you about how accurate that particular model is. Okay? And there was, luckily, that particular model has had quite a lot of attention. And there's been some publicly available data from Florida that we can use to test this model. So in Florida, they gave us a few of the features for each person, and they gave us the COMPAS scores. So we actually have the outputs of these proprietary models, the outputs of the proprietary model, so we can test how accurate it is compared to our latest machine learning method from the lab. So COMPAS is the one that's used in the justice system, widely in the justice system, whereas the model that we've developed is, we just tested our latest machine learning method at the time. It was called certifiably optimal rule list. So this is a branch and bound method that produces certifiably optimal one-sided decision trees. So these are decision lists. They're like a series of if-then rules, and the model that we got from the Florida data was so tiny that it fits on the bottom of the PowerPoint slide. This is the whole model. And it says if you are a 19 to 20-year-old male, then predict arrest within 2 years of your COMPAS score calculation. Otherwise, if you're 21 to 22-year-old and you have 2 to 3 prior offenses, then predict arrest within 2 years of your COMPAS calculation. If you have more than 3 priors, predict arrest. Otherwise, predict no arrest. Okay, so it's so simple looking that we thought, well, how could that be as accurate as this fancy proprietary model that these counties pay hundreds of thousands of dollars for each year? So we said, okay, fine, we'll just test it. We'll take the data from Florida and we'll just head-to-head do it. And this is what we found. So this is accuracy. This is COMPAS, and that's corals. And then the different colors here are different folds of the data, because we do 10-fold cross-validation. So it's just telling you which fold of the data it is. And hopefully what you'll see here is that they're about equally accurate. There's pretty much no difference between the proprietary model and that little model that I showed you on the previous slide. And not only that, it doesn't matter which machine learning method you try, they all seem to perform the same. And some of these are very complicated machine learning models, like this is boosted decision trees and support vector machines and random forests. So, I mean, these can be very, very complicated black box machine learning models. And again, some of them they're black box because they're complicated, and then some of them are black box because they're proprietary, but all of them are as equally accurate as that little model I showed you on the previous slide. Okay, so we're not gaining any accuracy benefits from using more complicated models here. Okay, so as I defined earlier, an interpretable model is when you use a model that is not a black box. There's this field of machine learning that's arisen, which is explainable machine learning, which is when you use a black box and you try to explain it afterward. So this is what's also called post hoc modeling. So to do post hoc modeling, you start with a black box, and then you either create another model that explains it, that approximates it, and you say, okay, this is an explanation of my black box. Or you take the black box and you take various kinds of derivatives of it, or you try to visualize the black box and show what part of the input the model's paying attention to, and you say, okay, that's what the model's doing. But the problem is that having a model that's actually interpretable is like a chasm away from having an explanation of a black box. And I've given a bunch of reasons here. The first one is that when you trust a black box predictive model, it means that you trust the database that it was built from. Now, I'm happy to trust complicated formulas, right? We do that all the time. What I don't trust is data, because every large database I've ever come across has had some serious problem with it, like confounding or other things like that, or noise or mislabels or something. Another reason that interpretable models are not the same as explanations of black boxes is this reason I call double trouble, because it forces you to rely on two models instead of one. You have to rely on the black box and its explanation. And these two models actually have to disagree with each other, because if they don't, then you don't need the black box. You could just use the explanation, right? If they're always the same, if the black box is always the same as its explanation, you can throw away the black box. You just use the explanation. And so they have to disagree with each other. And if, sometimes people are happy, they say, oh, look, my explanation model agrees 90% of the time with the black box. Well, that's not good enough, because that means 10% of the time I can't trust the explanation. And if I can't trust the explanation, then I can't trust the black box, and then I have nothing to trust. Also, the typographical error problem that I talked to you earlier about with Glenn Rodriguez, that does not go away when you explain a black box. And then again, the bottom argument I think is the most powerful, which is that if you can produce a model that's actually interpretable, why should you try to explain a black box? You don't need it, right? So we have COMPAS that's been used around the justice system, but for all the arguments about COMPAS and its fairness and its racial bias and all that, why do we need COMPAS? Because we have much simpler models that we can argue about. Okay, so let me talk a little bit more about these approximation models. This language started around 2016, I think, where people decided that approximations were actually explanations. So here's an example of a black box model. It's called f of x. This is a model that predicts recidivism. It depends on only age and the number of prior crimes that someone's committed. Okay, so it does not depend explicitly on race. It might depend implicitly on race through these variables, but it doesn't depend explicitly on race. So then what could happen is that somebody could construct an approximation of the black box, call it an explanation, and say, okay, because my model, f tilde of x, approximates my black box, and it depends on race, then therefore my black box depends on race. And you could say, well, this is very silly. Nobody would ever do that, right? That's stupid. But the fact is that it actually might happen, and it actually did happen. So let me tell you the story about that. There's a very famous article that's essentially started the field of algorithmic fairness by the group ProPublica. And they claimed, and these are the guys who provided the COMPAS scores, by the way, and they claimed that COMPAS depends on race in a way that is not through age and criminal history. They claimed that there was an additional dependence on race. And so luckily, like I said, they provided the data from Florida so we could figure out what was actually going on. So here's what they did. They showed that the false positive rates and false negative rates of COMPAS varied by race. And then they suggested that might not be a good comparison because they were very different from each other. And they said we should condition on age and number of priors and re-examine whether it still depends on race. So then they created a linear model that depended on age and number of priors, and they still found a linear model with a low p-value for the race covariate, indicating that COMPAS depended on race other than through age and criminal history. And so they concluded that COMPAS depends on race. Now, let's do that again, and I'll explain what I actually think happened here. Okay, so false positive rates and false negative rates vary by race, and they said and what I think happened, of course, here is that this is actually a property of the data, not necessarily the model. In Broward County, the blacks in the database are younger and they have more priors. So that's why you have to condition on age and number of priors. And so they did that, which makes sense. And then here, they then approximated the black box with a linear model, which had a low p-value for the race covariate. But here's where I think they went wrong. I don't think COMPAS is linear in its covariates, and in particular age. And so their conclusion then that COMPAS depends on race in a way that's not through age and criminal history, I think might be incorrect. So let me tell you what, so this actually, when this whole thing happened in 2016, it kind of freaked me out because I saw the ProPublica article, and I had just finished writing a paper for the Journal of the Royal Statistical Society on interpretable models for recidivism prediction. And we wrote this, we published this paper, and it basically said you don't need a black box. And then when the ProPublica article came out saying that there's this black box that depends on race, I looked at it and I was thinking, but you don't need black boxes in in for predicting recidivism, and race doesn't help. You can add race in, but it doesn't help you predict recidivism. And so this article is wrong, and I figured nobody would pay attention to it. But then it blew up. It became this huge thing, and it started this whole field of algorithmic fairness. And then I thought, I really want to know what's inside COMPAS. And so that's why we tried to figure it out. And so this is what we think. Okay, so this has been really fun for us to do this detective work. So we think that inside COMPAS is a dependence on age that is not linear, and in fact we think it's approximately a linear spline. So it's a nonlinear model with a few pieces here. And I'll tell you, you might be thinking, well, how did you get something so specific, right? Because COMPAS is a proprietary formula. How do you get this? And I'll show you the answer. So what we did was we plotted all the individuals in Florida that got their COMPAS score taken within this few years. And for each person, we put a dot. So this dot represents their age versus their COMPAS general score. There's actually two, by the way, there's two COMPAS scores. There's a general score, which predicts arrest, and a violence score, which predicts violent crime. So that's why there are two models here. So this is how we think COMPAS depends on age for the general score, and this is for the violence score. Okay, so here I'm showing you, like I said, each dot is a person, and this is their age versus their COMPAS score. And I hope you can see this, but there's pretty clearly a lower bound, right? There's nobody in their 20s who's going to get a COMPAS score that's down here, right? And same with the violence score. There's nobody in their 20s who's getting scores down here. So we think that this lower bound here is how COMPAS may depend on age. And there's a few outliers, which could be data errors, but there's a sort of a general trend that we're seeing there. And if I zoom into those two curves there, you can see there's the pieces of the linear spline right here. And then where the dots are darker colored, those are where there's lots of people who end up with exactly the same COMPAS score value. Okay, so we think that, and these people, by the way, all of these people on these lines, they have no criminal history. So it's possible, and then they have the lowest COMPAS score for their age. So it's possible that for those people, these are the only contributions to COMPAS is just from their age. Okay, so we think, and then we were like, okay, fine, let's figure out whether COMPAS depends on race, other than through age and criminal history. So we did sort of a machine learning analogy of ProPublica's analysis, where we literally subtracted out these splines so that everybody was starting at an equal level. And then we used machine learning with and without race to try to figure out whether there's still this residual dependence on race, and it wasn't there anymore. So in any case, I can't tell you whether COMPAS depends on race, but what I can tell you is that ProPublica's analysis is not correct. Okay, so in any case, let's go back to explainability versus interpretability. We don't, again, explanations, they're not, approximations are not explanations. They don't actually tell you what the model's doing. They can get variable importance very, very badly wrong, as we found out with the ProPublica story. And then another interesting thing about the ProPublica story was that they paired these individuals, to make it look like COMPAS depended on race other than through age and criminal history. So they had these pairs of people where you would see a young black woman with a very low criminal history being compared to like a seasoned armed robber who's committed, two armed robberies, attempted armed robbery, and so on. And you're thinking, well, how did this young black woman get this high score and this white man get this low score? And it turns out that there's another thing at play here that's actually even more powerful you know, than COMPAS itself, which is again typos. So with COMPAS, you have 137 factors entered by hand for each survey. Even if you have a 1% error rate, there's a 75% chance of at least one typo on a survey, which is a really serious disadvantage to complicated and proprietary models. And I gave you the example of Glenn Rodriguez earlier, where it leads to sort of years of extra prison time. And so we were thinking, okay, how often does this happen in Florida, right? Is this a serious thing that's going on in Florida? And it turns out that it actually is. So I'm showing you a number of people here with the lowest possible COMPAS violence decile score. So this is like the lowest score you can get. And this is the number of prior crimes they've had. Here's some selected prior charges, and these are subsequent charges after the COMPAS score was calculated. So here you have people with like 22 prior crimes, like aggravated battery with a deadly weapon and, um, you know, aggravated assault with a deadly weapon, battery on a law enforcement officer, murder in the first degree. I mean, it's shocking. How did these people get the lowest violence decile score? And that list is, I've only shown you the top of the list. It goes on. So here's more people, like here's people with like 36 prior crimes, 20 prior crimes. I mean, it's kind of shocking at how many potential, I mean, I can't explain these other than through data anomalies. Okay, so back again to interpretable versus explainable. So I've already talked about, a number of reasons why they're different. Let me talk a little bit more about explainable. So this picture is from the DARPA Explainable AI BAA. And it's supposed to illustrate that explanation effectiveness has to go down as accuracy goes up, right? That there's this inverse relationship with learning performance and your ability to explain something or other. But see, this, I just didn't go for this picture. Like this to me looks like somebody made it up, right? There's no problem associated with this. The axes aren't quantified. None of it's meaningful for any problem. And it looks like Trump with the Sharpie, it just sort of like made it up. And I was just thinking, okay, I don't know where they got this, but okay. Well, it looks like what they're trying to do is run different machine learning methods on one data set and see that there's a trade-off between explanation effectiveness and learning performance. Because you add more constraints, you get worse performance. But the truth is that that's not the way you're supposed to do data science, right? When you do data science, you're supposed to look at your result and go back and fix your data. And if you do that, then as your ability to understand what's going on improves, you actually get better performance, not worse performance. So that's kind of rubbish. And then also, even in real problems, the trade-off doesn't happen like this, like I showed you in Florida with the COMPAS data. In fact, it doesn't matter what you do, you're not going to get more than 74% accuracy on the data set. And then I couldn't figure out here whether they're talking about explaining black boxes or if they're talking about, actually building interpretable models. And it turns out they were talking about explaining black boxes. They didn't even consider interpretable models. So I went to the trouble of writing this paper back in 2019 to try to actually explain to these people, including these DARPA program officers, why actually there's this big difference between interpretability and explainability. And I outlined a number of things that I've talked to you about today, and in particular, the fact that typos haunt black box models, that black box models still force you to trust the data set, even if you have an explanation for them, that you have this problem I told you about called double trouble, where you have to rely on a black box with an explanation, which is two models instead of one. So if one of them goes wrong, you're stuck. and of the fact that these models actually have to disagree with each other. Otherwise, you don't need the black box at all. And also the fact that the explanations are not really explanations. They don't use the same variables as I talked about with the ProPublica scandal, where ProPublica said that COMPAS depends on age, criminal history, and race, but their analysis was wrong. It probably only depends on race through age and criminal history, but because they tried to explain a black box, they didn't understand this issue with variable importance that happens, that an explanation model doesn't have the same variable importance as the black box. And then, of course, this important point, which is that if you can actually produce a model that's interpretable in the first place, why are you going to the bother of explaining black boxes? Do you really want to extend the authority of the black box by claiming that you can explain it, or should you just ditch it and put in a very, very simple model that people can understand and use and adapt to new situations? So I want to spend the rest of the talk just very briefly overviewing 2 out of the 4 long-term projects that are going on in my lab. I already talked to you a little bit about the 2 helps to B score, which was designed with our scoring systems projects work. So the scoring systems projects work, that's actually a cutting plane method that leverages elements of branch and bound to try to produce models like the 2 helps to B score. And the other topic I won't talk further about is I have a matching project for causal inference where we're trying to match treatment units and control units in a way that's like trying to find almost identical twins in large data sets. But today I'm going to focus on these 2 projects, the optimal sparse decision trees and interpretable neural networks. So the optimal sparse decision trees project, I've been working on this since, I would say 2012 or so. I just put a couple of recent papers there. But let me tell you a little bit about it. So decision tree optimization, that's been popular since the very beginning of machine learning. And the main problem with decision tree optimization is that the algorithms that people have been constructing are greedy algorithms. They try to, construct them from the top down. So here's me kind of greedily constructing a model for whether I'm going to hit whether I'm going to hit traffic on my way back from work. And so I might say, oh, rain is an important factor for whether I'll hit traffic, so I'll just split the data set into pieces. And then I'll say, oh, if it's raining, then I have to look for construction. If there's construction, then I'll split into 2 pieces and then predict traffic if there is construction and no traffic if there's not. And the problem is these algorithms generally construct the trees from the top down. So if you make a mistake at the top, there's no way to undo it. You can't sort of go back and sort of undo it. And so you end up with these trees that are overgrown with a lot of extra splits trying to undo the mistake they made at the top. But the problem is, of course, that the space of possible trees is enormous, right? You can think about this huge factorially growing space and trying to optimize over that space, and that's really hard. And so people have been trying to use things like mathematical programming solvers to solve these, but they're really not designed for this task. And despite the wonderful work that's been going on in this area, they just haven't really been that successful with this. And then neural networks are also being used for pretty much everything, but they of course don't work for this task either because they're really not meant for this task at all. And you can't really prove optimality with the neural network. That's really hard to do. You can get that with a solver, but not a neural network. Okay, so the optimization problem we're interested in is to try to minimize misclassification error regularized by the number of leaves in the tree. So keep the model accurate, keep the model sparse. And we need to solve this to optimality. We want a provable optimality, or at least a quantifiable optimality gap. And we don't want to do greedy splitting and pruning. That's not going to get us there at all. So the key that we found is to use a very efficient branch and bound strategy combined with approaches from computer systems. And I'm just going to put up an example of a decision tree. This is an example. Like if you optimize this thing fully, this is the result, right? It's an actual tree. This is an example of an optimal tree we constructed on the Florida data that I was talking about earlier in the talk. Okay, so our main tools, our sort of sledgehammers to do this are bounds. So it's a collection of theorems that reduce the search space by showing that some partial trees can never be extended to form optimal trees. So for instance, if you're trying to construct an optimal tree here, if you try to split on something that's really not very common, like tornado, then the algorithm, these theoretical bounds will kick in and say, no, you can't split on tornado because there's not enough data going into that leaf to allow that to be part of an optimal tree. And so it'll say, nope, no tornado, you're not allowed to do that. And not only that, but you can never extend tornado to be, extend this tree with the tornado in it to be a full optimal tree. So you can just remove that whole part of the search space. And then there's also another theorem that says, okay, if you don't have enough accuracy in each leaf, then it's not going to, if you have no capability to get enough accuracy in each leaf, then it's not going to be an optimal tree. So get rid of it and all its descendants again. Or else if you have too many leaves for how accurate the tree is currently, then again, we can prove that that's never going to be extended to form an optimal tree. And another trick we do is to represent a tree by its leaves. So here I've represented the tree in the normal way we think about it, but the truth is that in the code, we don't represent it like that. We represent it literally as a set of leaves. So here, this leaf is rain yes, construction yes, traffic yes. So that's here. And then this leaf is rain yes, construction no, no traffic. And so instead of actually writing the tree in, actually storing the tree like this on the right, we actually store it like this on the left. And so then when we're done, we go back and we can construct the final tree afterward. But by just storing the leaves, you can operate on the leaves much more efficiently because it's a set. And then we also have a data structure that keeps track of permutations, because you see, if I find the same collection of leaves in an isomorphism, like a permutation of these leaves, then I say, okay, well, I've already dealt with that before. Like I've already seen that before, so I don't need to do it again. And so it prevents me from repeating my computations if I've stored all the permutations of the trees that I've seen so far. So now what happens is when we have a new tree, we go and look it up in this permutation map and decide whether or not we've seen it before. And if we have, we're done with it. If we haven't, we put it in the map so that we won't repeat our computation in the future. Okay, another thing we do is we store all of the data. We store a bit vector associated with each leaf that represents the data that goes into that leaf. So for instance, the first data point in the database is rain and construction, right? And so that data point there's a bit that's 1 for that first data point there. That's the first trip home I've ever taken where I, where it was rain and construction or something. And then each data point gets represented here. So like the second data point it was raining and there was no construction when I was driving home from work. And so that's where that bit comes from. And so by storing these bit vectors with the leaves, we can actually carry information and operate on the trees very, very efficiently. So for instance, if we've got a lower bound on the objective for one leaf and we want to carry it down to the leaves we're constructing below it, we actually can take that bound and carry it down, and then also carry down the bit vector of who is captured by the leaf, and that sort of then we don't have to recompute it. It helps a lot with incremental computation. So we just carry these computations all the way down the tree as we're constructing them. Okay, so the combination of the strong analytical bounds, the leaf-based representation, the permutation map, and the caching of intermediate results and incremental computation, they all kind of work together to really give us a very fast implementation of these optimal sparse decision trees. And at the moment, the current code is pretty nice. It actually can handle lots of different objective functions. So not just accuracy, it handles balanced accuracy and weighted accuracy, and also area under the curve and partial area under the curve. It handles F1 score. And actually it handles any objective that's monotonically increasing with the number of false positives and false negatives. So it's actually very general. And we changed it now so it's doing more of kind of a dynamic programming approach and storing subproblems and not going back to the subproblems that it's seen before, and so on. So you can check it out if you're interested in this kind of in these kinds of problems. And so I think for the very last part of the talk, I want to just talk a little bit about interpretable neural networks because it's always fun to end with images. So one problem I mentioned earlier about explainability of deep neural networks is that the explanations they don't always agree with what's actually going on underneath. So this is a neural network that is giving you evidence for this picture of an animal being a Siberian husky. And the explanation is what's called a saliency map, which highlights part of the image, and that's supposed to give you confidence that the network is doing the right thing. Okay? So you could say, I think the network's doing the right thing. It's highlighting exactly the part of the image that you would expect to be able to classify Siberian husky, and so I trust it. But the problem is that if you ask the same network to give you evidence that this image is actually a musical instrument, it gives you almost exactly the same explanation. Like it highlights this almost the same part of the image here. So, it's really unclear what the network is actually doing, and the explanation is so incomplete that you just can't really trust what it's doing at all. So we thought, okay, well, the computer vision people, I mean, these guys are working with they've invented the deepest of the deep in terms of neural, the most complicated models that have ever existed are these deep neural networks for computer vision. And for computer vision, you're not going to be using a decision tree on the pixels, right? That doesn't make any sense. So we need to come up with a type of explanation that that sort of would actually work for computer vision. And so we thought, okay, we'll do case-based reasoning. Right? Case-based reasoning it's kind of like what Dr. House uses. I don't know how many of you have seen that TV show, but Dr. House he's a TV doctor, and he has a patient. He sees the patient, and he says, "Okay, this patient seems like a patient I've encountered in the past. That patient had these symptoms. My current patient has these symptoms too. Maybe it's the same disease." And then he says, and then the team during their differential diagnosis, they say, "No, this other patient had these other symptoms that match your current patient. So I think this patient looks like that other patient." And this is also it's kind of similar to the way real estate agents price houses, right? They say, okay, the price for a current house is similar to, well, the current house is similar to this other house in the same neighborhood in this way, so I'm going to leverage the price from that house and sold for this much and so on. So we said, okay, let's try to do that for images. All right, so I don't know anything about birds. I'm not a bird watcher. And so working with this bird watching data set has been wonderful for me because the network actually has to explain what's going on. And so here the network is explaining why it thinks this bird over here on the left is a clay-colored sparrow. And what the network's doing is it's highlighting different parts of the birds that it thinks look like prototypical parts of clay-colored sparrows. So it's saying this part of the bird looks like, so this part of the bird here looks like this part of that bird. And this bird is a prototypical clay-colored sparrow. And this part of the bird looks like this part of that bird. And this bird is a prototypical clay-colored sparrow. And then it makes a comparison over here and a comparison over here. I mean, the network does not know that this is the head of the bird, this is the belly of the bird, the wings of the bird. It doesn't know that. It's just looking for parts of the image that are similar to parts of other prototypical images it's seen before. And it's making that judgment and saying, this is why I think this looks like that, this looks like that, this looks like that. And so that's why I think it's a clay-colored sparrow. And so as we were designing this network, we thought, okay, because the network is doing all these comparisons, right? It's saying this looks like that, this looks like that, this looks like that. We think we'll just call the paper "This looks like that." So that's what we did. So this looks like that, okay? And I'm going to give you a little more details about how it works. So here, the network is trying to explain to me why this bird is a red-bellied woodpecker. It's giving me all the evidence of why it's a red-bellied woodpecker. And there are 20 red-bellied woodpecker prototypes, so 20 prototypical images of red-bellied woodpecker. I only showed 3 of them here. And what the network is saying is that it thinks that this part of the bird looks like this part of this bird. Now, how similar these two pieces are is given by this number points, or 6.499. So 6.499, by the way, is a really big number as far as these similarity measurements go. So it says, I think this is really similar to that. And then this number over here is associated with the importance of this image to the red-bellied woodpecker class. So in other words, there are 20 numbers here in this column that tell you how similar the current bird is to these past birds. And then there are these series of numbers that tell you kind of how important each of these prototypical birds are to the red-bellied woodpecker class. And so when you add up all the points that you get, this particular class gets 32 points. So that's how much evidence we have that this bird is a red-bellied woodpecker. And then we actually can ask for the evidence for all of the other classes of birds. So here, for instance, we're asking what the evidence is of it being a red cockaded woodpecker. Now, interestingly, red cockaded woodpeckers do not have red heads, but their feathers, the pattern on their feathers kind of matches our bird over here. And so the network is trying to use as much evidence as it can from doing the comparison between the feathers of the current bird and all the prototypes of these red cockaded woodpeckers. But in the end, it just can't get enough points, and it has only like half the number of points as it did before. Okay, so we've been doing some comparisons with black box methods, and by the way, this method, it takes any black box and it can turn it into a case-based reasoning classifier. And the black box accuracies range between these two values, whereas the interpretable model, it gets you, a little bit higher in the base case and a little bit lower for one of the other neural networks. But essentially, if you combine all the interpretable networks together, you still get something interpretable, and you get even a higher accuracy than all the black box neural networks. So you're not sacrificing any accuracy for interpretability here. So even for computer vision, we can still have an interpretable model of the same accuracy as a black box. Okay, so yeah, that's it. Thank you.
Oh, thank you, Cynthia, for this nice talk. And so we are now open to questions. And if you have a question, please use the chat and type in your question. Okay, so there's one question from Tito Hamam de Mello. You say that one problem with black box methods is that databases that feed them cannot be trusted, but presumably interpretable models also must rely. Okay, this is moving too fast. I'm sorry. I lost the screen.
Yeah.
Must also rely on databases. So doesn't that lack of trust also affect the conclusions from interpretable models?
Yeah, so the thing about the interpretable models is that doctors don't have to trust them. They can actually look at the factors in the model and decide whether or not they want to trust them. So if the models agree with their domain expertise, they can choose whether to trust it. But then if the model has something funky in it that reflects some badness in the database, then they don't have to trust it. So yeah, so the idea is if you could see the internals of the calculations, then you can decide whether to trust it. Okay, optimal sparse decision tree. Is your method not a mathematical programming-based method? I mean, it is in the sense that it's all custom, but it's not using a solver, right? It's not using Cplex, it's not using Garobi or anything like that. It's actually a custom, custom solver just for this purpose. And because it, it uses its own bit vector libraries and has its own ways of using computational reuse and so on, it's much, much faster, like orders of magnitude faster. Symbolic metamodeling for interpretability, which is able to build a symbolic representation that approximates the black model's output. So again, when you approximate the black box model's output, you can really goof up problems like variable importance. And I tried to stress that in the ProPublica example where they sort of approximated the black box by something and then claimed that the properties of the approximation carried over to the black box. And that wasn't true. And it caused a huge amount of problems. And so I'm not really into approximating black box models for high stakes decisions. I think for low stakes decisions, you don't really need interpretability and you don't really need explanations of black boxes. But for high stakes decisions, I think you probably need to think about whether you can just throw out the black box and replace it with something else. Okay, would you want the authorities to use your interpretable recidivism prediction model? Not the one in the slides. I don't want the authorities to use the one in the slides. We actually have a new paper out that's on arXiv on interpretable and fair predictive models for recidivism. And what we advocated in that is that we did a comparison of some of the models that are used in the justice system, including the Arnold PSA and COMPAS. And the PSA wasn't too bad, but we found that we could improve over the PSA by using models that were specific to each location. So we actually think that you should retrain your model depending on the location because, like we were working in Kentucky and Florida, and in Kentucky, the age curve, like the way that recidivism depends on age, it's different than the way that it depends on it in Florida. In Florida, there's a steep drop off, whereas in Kentucky, it's sort of like wavers around. So I don't want the authorities to use necessarily any model for everybody. I want them to sort of think about what's right for their particular location and the way that that location would benefit from a customized model. Let's see, even if it's better than COMPAS, can't the end user use the interpretable prediction to justify an unjust decision? Yeah, that's a good point. Yeah, that's true, actually. I never thought about that. That's true. I suppose they could make an argument that that this interpretable model should have been the one that was used. I know that, I mean, right now there is at least one lawsuit going on against COMPAS, but it's not because it's not interpretable. It's because of some other thing. But yeah, that's a really good point. Thank you a lot. Where's
So she's the next.
prediction and its interpretability? Okay, or is improving the average case prediction? No, I think you're right. I think you're right there. Okay. Is it possible to explain your interpretable optimal decision tree? I'm talking about generalization-bound confidence intervals, etc. Yes, it is, because the VC dimension of the VC dimension is the number of leaves in a tree. So you can actually get a generalization bound, so a probabilistic bound that goes from training to test error. You can actually get a bound like that depends on the VC dimension, which is the number of leaves in the tree. So you immediately get a generalization bound. And it's very well established that the error on the training set is not too different from the error on the test set when the models are simpler, when they're from simpler VC classes. So you do get that. Finally, how do you compare your approach to random forest? Okay, so what random forest is when you construct a whole bunch of overfitted trees and you average them together. So random forest is not particularly interpretable. I suppose if you really liked combinations of trees, you could try to take up a bunch of optimal trees that are weighted differently and average them together, but that's not really what we haven't really worked on that before. Okay, so why should we find the optimal one instead of having a forest and returning a probability? So you can get probabilities from one tree. There's actually, if you want to get probabilities in the leaves, you can get them directly by computing them. But there's also fully Bayesian models if you want probability distributions over trees. So there's something called, there's Bayesian rule lists and sparse and scalable Bayesian rule lists that produce whole posterior distributions over trees. So you can get full probability distributions and full posteriors. Okay, when you move from prediction to prescription, can you also have interpretability? Okay, so the answer is I I think so. So there is a paper that optimizes one-sided decision trees over lots of different cost information. So that's a way to kind of move from the just prediction aspect to the actual decision-making aspect, so that you're considering all these different costs associated with the decision in the actual tree structure. So the second question, in reinforcement learning, could you explain decisions as opposed to predictions in a similar way to what you did for predictions? Now, reinforcement learning is a whole different kettle of fish than what I was just talking about. And I will admit that that I've been struggling to understand how to do interpretability in reinforcement learning. But there has been some nice work by, I think her name is Ofra, I can't remember her last name offhand, on interpretability for reinforcement learning. And there's also a company that's doing a really nice job in uh, understanding chess decisions made in chess. But those problems are not really machine learning problem. They're not really the kind of machine learning problems that I was talking about, where you've got a static data set and you're trying to explain like a single prediction. For reinforcement learning, you have to explain what's going all the way down the line, so that's much more complicated. Okay, FICO has not been able to use machine learning to improve on their regression-based scoring models. What do you see as the difference between classical regression approaches and interpretable machine learning? So I actually entered a competition that was last year. It was the FICO Explainable Machine Learning Challenge. And we also took the data set from FICO and we were able to get an interpretable machine learning model that was just as accurate as any neural network that we could construct on FICO's data. So in terms of the difference between classical regression and interpretable machine learning, I view regression as part of machine learning, but in order to make it more interpretable, we add more constraints. So for instance, with the scoring system project, we're doing essentially logistic regression, but with extra constraints, which are these constraints on sparsity, and also constraints on the fact that all the coefficients have to be integers, right? They all have to live on an integer lattice. So you're actually solving a much harder optimization problem to gain that level of interpretability that wouldn't necessarily be true with a regular logistic regression, because it's not sparse and it doesn't have the integer coefficients. Okay, I've been working on interpretable models in healthcare. In an effort to create robust and parsimonious trees, I've been using random forest to select the variables that I use for the decision tree, and I limit the size of the tree, variables included, and levels. How would that compare to the optimal tree? Okay, so that's exactly the question that we were trying to answer with our optimal sparse decision tree project. And then he's saying, do you think the approaches would be similar? So the only way to actually answer that question is to actually run an optimal sparse decision tree method, because, or like a certifiably optimal decision tree method, because you can't determine how close to optimal your method is until you compare it to something that's actually optimal. And in some cases, there could be, in some cases, CART is actually doing, just as good as the optimal tree. But in other cases, like when you have imbalanced data, CART is terrible. Like CART often just predicts, like if you have very imbalanced data, like you have just a few positives and a ton of negatives, CART just predicts negative for everybody, and no matter how you adjust it. So there's a huge gap there between the CART solution and the optimal solution. And unless you actually solve the problem, you don't know what the gap actually is. Okay, what are the biggest roadblocks to implement interpretable models? So the first one is that, again, it's really hard to construct these optimal models, because if you add in a lot of constraints, like the constraints I was talking about, like sparsity for decision trees, and the integer constraints on the regression coefficients, then you have to actually solve these optimization problems, and that's hard. And a lot of companies don't have the capability of solving those problems. Another roadblock is that people don't want interpretable models. They actually want to use models that are complicated because they can sell them, right? It's really hard to sort of, hand somebody a little tiny model and say, hey, I spent $1 million constructing this, here you go. Instead, you want to say, there's a piece of software. It's really good. It has this model in it, you know. So I think that's an obstacle to implementing it. And also, like a lot of machine learning people have this attitude where they don't have to know anything about the problem. They can just step in with their fancy tools and run it. And you know, and they don't actually have to know anything about the problem. But that's not really how you should do data science. Or you know, any really good data science or statistician would never say, oh, you just step in and you run your thing and here you go, here's the answer. I mean, you actually have to digest the solutions and think about the problem. And that's sort of an attitude problem we have in machine learning. Oh, okay, so David Clark. Okay, so I'm sorry, I didn't understand the question. Okay, so maybe I'll take a look at that afterward, or you can try to ask it. You can take yourself off mute. Maybe I'll try to answer this last one first, and then we'll have you take yourself off mute, and we'll do that. Okay. Are the trees built by optimal decision tree methods unique for a given data set? No, they're definitely not. In fact, you can have many optimal trees that are, you know, they're all equally optimal. There's no reason, this is not a convex problem, so you don't expect uniqueness. And especially if you have two features that are identical, they're completely interchangeable. So no, they're not going to be so unique. And in fact, for regression, they're not unique either. Even in regression, if you have two features that are very highly correlated with each other, those two features can be interchangeable. A follow-up query. How sensitive would the interpretations be if deployed in an online setting? So I mean, like I said, if you have multiple trees that are equally good, then they could be very sensitive to, you know, if you swap between these optimal trees, then you know that could be an issue. But the idea is, for at least for the medical projects that I've worked on, is that the doctors look at the models and they decide which one they want to take, and it agrees with their intuition. And so they're not swapping between these models in an online setting at all. They're using a model that they actually trust, and then they validate it before they use it on other data and so on. Okay, deep networks follow the double descent phenomenon. Does such a thing exist in decision trees? No. The double descent phenomenon is just a super weird thing that I don't really understand why it happens, and I don't really think anyone else does. And it has to do somehow with the way that gradient descent is operating in it's only in neural networks, and it doesn't happen in any other method. So, I mean, people have tried to artificially find it in other methods, but it didn't really work. So, no, it doesn't happen in decision trees. Do you think there are cases in which you have actual nonlinearities, complexities, interactions, and you simply cannot have a simple model to do the work? Yes, there are certainly cases like that. For example, where the ground truth is a complicated model and you are trying to approximate it. But luckily, that's not really the case in real world problems. In real problems, there's usually some degree of fudginess, which I call a Rashomon set. So it's some degree of uncertainty that you have that allows you the flexibility to have lots of good models. And then the idea is that if you have lots of good models, at least one of them hopefully is interpretable. And that's kind of what we're seeing in reality. So that's kind of what that's the answer to that's my answer to your question. So yes, there are such cases in theory, but in practice, luckily, there doesn't seem to be. And I can say that having worked in power grid reliability, lots of different healthcare problems, criminal justice, now I work in material science. So no, I've always seen some level of fudge factor that I can leverage to get a model that's interpretable.
Just to, we're already at 15 minutes late, and I think there's maybe a last question or so, and then after this, maybe we should cut off the questions. And if anybody wants to continue, if Cynthia is available, we can do that.
Yeah, so I think anyone should obviously feel free to step off when you want to, because I'm just answering questions. But I'm just going to sit here and answer questions until they're done. So we can just do it that way.
All right, thank you, Cynthia.
Yeah. Um, okay, regarding interpretability, is it is often connected or confounded with additional tasks, for example, measuring variable importance or performing robustness sensitivity analysis about what to do and to change the classification outcome. What's your take on this matter? Can optimal trees help doing these analysis? That's a really good question. Um, so I have a separate project on variable importance where we're not just measuring variable importance for one model, but we're measuring variable importance for all good models. So all models that are kind of in this Rashomon set of possible good models. And then there you get kind of a range of variable importance for any variable. But if you want to understand the variable importance for one model, what you can do is, and this is a trick of Leo Breiman, you can take that variable and you can scramble it. You just take that variable, you just mess it all up, and then you recompute the accuracy. And then you look at how much the accuracy decreased between when you didn't have it messed up and when you messed it up. And that tells you how important that variable is for that model. And so that it's kind of you can do that for black box models and interpretable models. So variable importance to me is something that's nicely understood even with black box models. So I kind of like that. But of course, if you have like a simple scoring system and you have like 3 points for this variable and 2 points for this variable and 1 point for that variable, then you can see it like right on the screen there. Um, and then you also mentioned sensitivity analysis about what to do to change the class. So that's called counterfactual explanations now. And I think, I think decision trees could help with that, but I'm not really sure how. Like you would have to figure out how much you would change the variable to make it go down a different path in the tree. But I think you still have to do like a little calculation to kind of show you what, if you're going down this path, how do you change a variable to go down this other path? So you would still have to sort of think about that carefully. Okay, so thank you. Yeah, double descent is an artifact of SGD, yes. Okay, how can constraints the parameters of the model, relative simple as a decision tree or a linear regression to be integer give very good accuracy? If the constraints are relaxed, you get better accuracy in the training set. So it's like you do a very good regularization. Yes, that's actually a good point. So making the coefficients integers actually gives you some level of regularization. I actually there's actually a lot of theory too behind these integer coefficients. For every model that for every model, I think it's up to 7 variables. Uh, for every real valued model that's up to 7 variables, you can actually produce an integer model that's it's actually the same. So you're not losing or gaining anything for the integer coefficients for smaller models, but just the fact that you're using a sparse model will give you regularization. I think the integer coefficients you basically just get for free, and they just help you interpret the relative magnitude of the importance of the different variables. Okay, I'll have to go and I hope I can keep this chat. I'll have to like take pictures of the chat so I can keep all the links that people are sending. Maybe I'll just do a little screenshot there to get some of the links. Although the screenshot's not going to allow me to click on it.
I don't know if they're sent privately to you, but usually Zoom can keep a record of the chats as well. But if they're sent privately to you, maybe not.
Oh, okay.
I might just stop the recording at this point, but we can continue. And we can also take people off the, maybe they can speak.
Sure. Yeah, that'd be great.
All
Yeah.
right.
Okay.